In this video, we will design a distributed cache. We will start with simple ideas and then evolve them into a detailed design. Let's look at a typical web application backed by a database. The client sends a request to the web service, which in turn sends a request to the database, and the result is returned back to the client. This works fine for typical web applications, but if your web application becomes very popular, you will start seeing a lot of requests. These requests will load your database, and overall latency will increase in the responses sent by the web service. It would be a good idea to cache some responses to overcome these problems. The cache will give two main advantages to our web application. Firstly, the responses to clients will be much faster. Secondly, the cache helps conserve resources and reduce the load on the database. How can we implement this cache? Let's formalize our requirements. We need to implement two primary operations, put and get. The put will store data in the cache under some unique key, and the get retrieves a particular data from the cache based on the key. As for non-functional requirements, we want to design a scalable, highly available, and fast cache. High scalability will help ensure our cache can handle more put and get requests, and be able to handle the increasing amount of data we may need to store in the cache. High availability will help to ensure that the data in the cache is not lost during hardware failures, and the cache is accessible in the case of network partitions. High performance is the number one requirement for the cache. Let's start with the local cache first. We begin with a single server and implement a primary in-memory data store with limited capacity. We need to develop data structures and an algorithm for storing and retrieving data. Hash table can be used to store frequently used data as key-value pairs and retrieve them in constant time, until we reach the maximum hash table size and cannot add any more elements. We must evict some old data from the hash table before adding new one. What data should be evicted? There are many different approaches to this, called eviction or replacement policies. One of the popular implementations is the least recently used policy, as hash tables do not track which data has been used recently. We need one more data structure to track this. The doubly linked list can be used for this purpose. The item at the head is the most recently used, while the item at the tail is the least recently used. Now let's run the simple simulation that will help to understand further. The cache and the list are initially empty, so we keep adding new items to the cache and to the list at the head position. 5 items have been added, and the cache has become full. Now get operation has been called for item B. We need to move this item to the head of the list. Right after that, item A has been accessed, and we moved it to the head of the linked list. Remember, the item at the head position is most recently used while item at the tail is least recently used. Now the put operation has been called for a new item F. We first delete the item at the list tail and from the hash table because the cache is full. Then add item F to both the hash table and the list at the head position. And we are done with the local cache implementation. Let's look at how to make our cache distributed. We can start with a straightforward idea, moving the least recently used cache we just implemented to its host. The benefit of this is that we can now make each host store only chunks of data called a shard. Because data is split across several hosts, we can now store much more data in memory. Service hosts know about all shards, and they forward put and get requests to a particular shard. But how does a service host decide which cache shard to call? Let's discuss a naive approach first, which uses the mod function. We divide the key by the number of available cache hosts. The remainder will decide which cache host will be used. But what happens when we add a new cache host, or some host dies due to hardware failures? The mod function will start to produce completely different results. Service hosts will start choosing completely different cache hosts than they did previously, resulting in a high percentage of cache misses. Hence, this approach is rarely acceptable in production systems and is usually used for testing purposes only. A much better option is to use consistent hashing. Consistent hashing is based on mapping each item to a point on a circle. We then take a list of cache hosts, calculate a hash for each host, and map it to the same circle. Specifically, each host will own all the cache items between this host and the nearest clockwise neighboring host. It can be counterclockwise, it does not matter much. When we need to look up what cache host stores a particular item, we calculate a hash, and move backwards to identify the host. And what happens when we add a new host to the cache cluster? As before, we calculate a hash for a new host, and this new host becomes responsible for its own range of keys on the circle. while its counterclockwise neighbor becomes responsible for a smaller range. Consistent hashing is much better than mod hashing, as a significantly smaller fraction of keys is rehashed when a new host is added or the host is removed from the cache cluster. Now we know how the cache cluster host is selected for both put and get, but who is actually making this selection? On the service side, who is responsible for running all these hash calculations and routing requests to the selected cache host? The cache client is that component. It's a small, lightweight library integrated with the service host and responsible for cache host selection. The cache client knows about all cache servers. The cache client stores a list of cache hosts in sorted order for a fast host lookup, and binary search can be used to find a cache server that owns the key. Let's recall the non-functional requirements we defined at the beginning of our design. We wanted to build a fast, highly scalable and available distributed cache. Have we built a highly performant cache? Yes. The least recently used cache implementation uses constant time operations. The cache client quickly picks the cache server using binary search in log(n) time. So, performance is there. But what about the other two, scalability and availability? Scalability is also there. We can easily create more shards and have more data stored in memory. But high availability is not there at all. If some shard dies or becomes unavailable due to a network partition, all cache data for that shard is lost, and all requests to that shard will result in a cache miss until keys are rehashed. The data replication mechanism will help us to improve availability. We can use leader-follower replication. For each shard, we will designate a master cache server and several read replicas. These replicas live in different data centers, so cache data is still available when one data center is down. By introducing data replication, we are able to increase